So we will talk about the shear and the interaction design in IDEA StatiCa RCS. As I mentioned, you would like to know the answers to several questions, how the program calculates inner lever arm for shear analysis, if we take it from response or where it comes from, what do we recommend for shear design of sections with axial force, because there is no recommendation of Eurocode. It is related to the problem of pre-stressed sections with the tendons located approximately in the middle of the cross-section. Such sections are actually located along the length of the beam in inflection points, and there is a zero or almost zero bending moment, and that's why the tensile resultant force is very close to the tendons and lever arm is very small. That's why shear reinforcement becomes higher than in the sections above the supports. The last question or problem which I would like to touch is the interaction of internal forces. When we speak about the problem of inner lever arm and other parameters related to shear, we have to start with the equilibrium conditions of the truss model. You can see the picture of reinforced concrete element with the shear force as the only load. So it is a theoretical case of pure shear. This shear causes the cracks, diagonal cracks, and it imposes compression into the diagonal struts. Due to that compression, we have a diagonal resultant force, and therefore we get a triangle of the forces here, and one of the forces in the triangle is the force in the longitudinal reinforcement. It means that this force has to be transmitted by some reinforcement, and it is transmitted by the stringers, top stringer and bottom stringer. I will refer this picture later. We can use this element to derive the equilibrium conditions, and based on these equilibrium conditions we can derive exactly the formulas which are mentioned in the Eurocode for example, the RDS or the maximum shear force before the diagonal is crushed. This, of course, is as I mentioned, is a theoretical case of pure shear. The code in the clause 623 paragraph 1 mentions that this inner lever arm corresponds to the bending moment in the element under consideration, and there is also a picture here which shows that this Z parameter is related to FCD. This coupling mechanism of the shear resistance and bending is taken as a main assumptions in the Eurocode. In case that we have sections without axial force, we can use approximate value 0.9 times D. Actually, if we have a section with axial force, I didn't find any recommendation in the Eurocode. But what about if we have the section loaded by axial force? This is a frequent case of pre-stressed sections or columns, bridge piers, etc., in which we simply have all the cross sections in compression. And another questionable case is biaxial flexure with the angle between resultant of bending, this is this one, and the shear force, which is in this picture intended as a vertical shear force in the direction of z-axis. If we increase this angle between these two resultants, then the lever arm, this Z, becomes smaller and smaller. You can see it in this picture. For example, here we have a resultant force in compression. Here this is the resultant force in tension, and because we have also this bar in tension. And then this lever arm Z becomes smaller when the angles, when this angle of these forces becomes bigger. In theoretical case, we have the angle 90 degrees as it is here, and according to Eurocode there would be no resistance of this, no shear resistance of this section, which is probably not the reality, not the real case. Actually, I said that this is a theoretical example, but I got some examples from our users in which they really developed the case that these two resultant forces were at the angle of 90 degrees. That's why we made a study. We monitored the influence of decreasing lever arm with increasing angle between those two resultants. And these are the results of the study. You can see this VRDS, this curve, and it decreases the strength here in kilonewtons when we increase the angle between these two resultants. If we reach 90 degrees, we have zero strength according to the assumption of Eurocode. Already in case that you approach approximately 30 degrees, and then the strength in shear decreases rapidly, and that's why the program would send you a message that the resultant of shear and flexure or the angle between these resultants exceeds the limit of 20 degrees. And you can take some action. The question is what to do then. Answer on this question is here highlighted in red color, but before I go for it, I would like to explain the procedure, how we check the shear force and design or make the assessment of the shear. First of all, we design it for the resultant force. When we have components Vy and Vz, we calculate the resultant force, and this is taken as the design shear force. All the parameters for shear check, like BW, D, and inner lever arm Z, are determined from the plane of strain in the sections assuming QLS conditions. So we calculate it in our response in RCS program, and we make following projections. D is the distance between the resultant in tensile reinforcement and the opposite concrete fiber in compression. This distance is projected into the direction of shear force, resultant shear force, and we measure the value D. Similarly, Z is inner lever arm, again projected into the directions of resultant shear force. BW then is the smallest width of the section in the direction which is perpendicular to the resultant shear force. We calculate it across the depth of D. We go step by step across this depth, and we calculate which BW is the smallest one. If the parameters D or Z cannot be determined, and there are some cases, for example this compression, if we have a section loaded in compression, then we use default values 0.9 D for inner lever arm. Or of course the user can define his own parameters, and that's the answer what to do then. We learned from the other picture, this one, that the forces in longitudinal reinforcement are applied in the top and bottom stringer. So in our opinion, it is good enough if we apply the Z as the distance of both stringers of the truss model. So Z can be taken from the geometry of the section. I prepared a small example. Now I show this very simple rectangular cross-section. First of all, we can see the internal forces. We applied both components of shear force and both components of bending moment. And if we go to results and in response, we can see these are the resultant forces in tensile reinforcement, and here we have it in concrete in compression. We can also see it here as the distance or the drawing in axonometric view. In this response, we calculated and then we projected into the direction of the shear force. First of all, I do not draw this, and we will see that in the table here, I can make it bigger. We have D570, it is the dimension line here, and also 498, it is the lever arm. Again, the dimension is here, and we measure it as a projection into the direction of the shear force, which is inclined at the moment. It means that when we find this response, we use the values exactly according to Eurocode as it is assumed in the paragraph I mentioned. In case that we cannot determine it, or we want to use the distance from the geometry as I explained in this truss model, we can do it as user-defined parameters, and this is done in reinforcement editor. If I go back to this, I go to reinforcement and I open here reinforcement editor. Then there is a possibility of user settings. If I go to user settings, cross-section, then we see that we have the possibility to input user value of shear with BW, user value of effective depth and lever arm, and of course also user value of angle theta. I will not do it now, but I will show it later in another example. If I cancel it, I go back. If we go to next point here, there is also the assumption in the program that the tensile force in longitudinal reinforcement caused by the shear is distributed uniformly into the bars which are enclosed by stirrups effective in shear. This is also something which is under the discussion. Some users ask about why we do it. Actually, we did it intuitively because when we derived the formulas for variable angle truss model, we assumed that it is similar as the wall, and if there was a reinforcement across the depth of the section, this reinforcement is enclosed by stirrups effective in shear, we should definitely use this reinforcement. Recently, we developed a new method here, which is based on finite element analysis, and the cross-section meshed by finite elements is loaded in pure shear as a strain, shear strain. And you can see the results. These red lines are the forces in longitudinal reinforcement. Actually, there was a longitudinal reinforcement in the middle of the section, and you can see that this alternative model, calculation numerical model, showed and confirmed our assumption that we have the reinforcement, longitudinal reinforcement loaded, I would say, almost uniformly. The other nice result of this analysis is that you can see that if we apply this shear force in the direction which I show now, then not only the stirrups which are parallel to this direction of the shear force, but also the stirrups which are transverse have some stress and resist some stress. And you can see that this is also important because of the inclination of the principal compression stresses in the concrete. We haven't implemented it. It is just quite recent model which we developed, but we can based on it in future. Another problem is the availability of the cross-sectional area which is effective in shear. You can see the picture here, and I can show it when I go to results and shear. Then we can draw the shear resistance region in case that we have a rectangular section or T-section, nothing more. It is quite difficult and not very reliable if we want to make it for general cross sections. But when we do it for this rectangular section, we see that based on the geometry of the section and the direction of the load, we can get different, I would say, available BW. This is 221, and BW calculated as this width is 304 millimeters. We use this 300 because, as I mentioned, we do not want to reduce it too much, but you can draw it, you can see what is the result if the strut can appear in the cross section. Sometimes if it's, for example, very slender T-section, a very deep T-section or I-section, then the strut can go even outside of the cross-section, which you can check. And in case that you are not happy about the geometry, you can easily change it in the user-defined values. So now we go to the design of bridge pier. I put here visual design so that I emphasize that we are able to investigate it by response and shear check in a very detailed way. First, what we want to show is are the examples of lever arm which are calculated or used as a default value or user defined, and we show it in the way that we actually show you the practical use of the response, that you get total control above your design. And if you are sure about the results, what is happening in the section, then you become self-confident and you can decrease your reserves in the design. Of course, you can make a more economic design. Let's open the file. I do not want to save it. This lever arm study of bridge pier. This is a real bridge pier, and the data sent by one of our customers. We can see, for example, the reinforcement here. This is nicely defined reinforcement, almost cat shape. I will discuss the way of the input later, but let's start with this example and with the current extreme E1. If we go to internal forces, then you see that we have all components of internal forces. We have quite small shear forces and torsion, but there is some. And now we can see the response. Let's go to results. and we see the response. Then maybe I can rotate the section to get a bigger picture, and we can see the resultant forces here, positions of resultant forces, and also D and Z calculated for this double bending. I switched off the strain of the reinforcement so that we can see also only stress. If I make it bigger, then you can see the direction, approximately the direction of the resultant bending moment. And now we go to, and now we go to shear, and we see the direction of the shear. And on the first view, we see that the angle is different, and the program sends you a warning that the angle between in-plane gradient of the strain plane and the resultant shear force exceed the limit 20 degrees, which could adversely affect the values of calculated effective depth and lever arm, and so on, so on. And note that the values of effective depth and lever arm can be defined in code settings. There are also other messages that shear is resisted by concrete, so actually the reinforcement is required in this case, in this extreme, in this combination of the forces, only according to the detailing provision, and also the maximum effective cross-sectional area of the shear force according to clause 6233 was exceeded, which means just the information that even if we increase the amount of shear reinforcement, then the diagonal would crash, and that there is no reason why to increase it in this for this case. But even if the angle is bigger, we still get reasonable Z and D parameter, and we have satisfactory check. Let's see E2 extreme, and you see that there is a completely different direction of the force. We can again see in the shear that we have some Z and D, but it is significantly different. I strongly recommend you to read the messages, the non-conformities here. Even if the design is satisfactory, the program sends you a message that the default value from code settings of the effective depth and lever arm was used to shear calculation, which means that we didn't find, or the program didn't find the response, or didn't find the parameters Z and D. If we go to response, you can see that we have all the cross-section in the compression. So we cannot find the tensile reinforcement, for example. That's why we cannot find the lever arm. In that case, it would be better if we define the parameter Z based on the geometry as I showed in the derivation of the variable angle truss model. We can continue in this shear in the next extreme. You can again see that we have exceeded a limit of 20 degrees. We have again different direction of the shear force. Next extreme similar, next extreme again. All of these are from the real bridge, from the customer. So this is not an example which I would just input because I wanted to show you. And this is the last extreme which I want to show. This is E6. And we can see that first of all, the response is completely, if I do not rotate it, then the direction of the response is completely different than the direction of the shear. And it is even not satisfactory. The shear is, as you can see here, 127%. In this case, again, the shear angle exceeded 20 degrees and so on, but the program found the response, as you can see here, and there is a flexure here, but the projection of the lever arm into the direction of the shear force is so small that Z is 28 millimeters only. This is actually not a real value which we would use for shear design. It is calculated purely according to EN code, so it is EN code approach. But if we see the projection of these two directions and the lever arm projection, then I would strongly recommend to use user-defined parameters. So in that case, we would go to the reinforcement, run the reinforcement editor, and use these user-defined parameters as I have shown. But this is not all what I want to show on this example. If we go to torsion check, we can see very strange equivalent thin wall section. Even if the torsion is very small, then if we check it, if we see what is happening in the section, or at least in the check done by the program, then immediately the program sends the warning, visually sends the warning. This is different shape of the section than this one. Actually, this is a user example from the user, and he didn't realize one important thing. We send you a message that it is not possible to create equivalent thin wall section for torsion check automatically from stirrups outline, because not all edges of equivalent section contain stirrup effective for torsion. In that case, we have to see what is happening in the reinforcement and reinforcement editor. We can go to, or maybe we even do not need to go to the editor. We can select the stirrup here, and we can see that all the stirrups which were input by the user are marked as the stirrup effective in torsion. Actually, that is what totally confuses the program. Because the stirrups are of very different shapes, and the program cannot identify automatically the thin wall section for torsion analysis. At the beginning, I told that this is almost cat shape of the stirrup. From that point of view, it is nice. But this is not a CAD program, this is calculation program. I prepared same example with different input of the stirrups. This is the other section. You can see here. Actually, from the point of view of the construction, detailing rules, and possibility to even insert such stirrup into the bridge pier, this is very I'm sorry for saying so, stupid shape. But it can generate, if I go to reinforcement editor, you can immediately go to user settings and torsion, and you can see that we have quite nice thin wall section which is identified by the program. And if I go to results, then in torsion we get a real shape which we expect and which is correct for the analysis. So the problem was that the shape of the stirrup was not specified as the stirrup for, I would say, structural design and member design, but CAD drawing. Now you can see that I have only one stirrup effective in torsion, and that's the one which goes around the whole, around the perimeter of the section. To get the same reinforcement, I added this, I would say, single links. These are these links which I added to the longitudinal, between the longitudinal reinforcement to make sure, and those are effective in shear in case that the critical section goes through and cuts these stirrups, then we get the same shear resistance. I said same, but it is almost the same. The problem is that if I go here to shear, and you can see in the picture that we identify some crossings here, and here of the, I would define it, actually we calculate the distance of the end of the stirrup and the points where the line which is projecting from this one, projecting from the centroid perpendicularly to the direction of shear force, and it crosses the stirrup's legs. And you can see that this is very small distance in between end of the stirrup and this point. It is small distance, so probably there is a problem with the anchorage. And you can go to the detailed results of stirrups. I can make it bigger. And you see that the stirrup number 8, branch of the stirrups 1, there is a reduction factor to 0.43, which means that the length between this crossing of the line, as I explained, and the end of the stirrups is smaller than anchorage length. So that's why we reduce the strength of this stirrup. Of course, you can make it so that the shape will be like this, and you can make a hook at the end, then it would improve the situation. But if you do it like this, then we calculate it. Now let's go to back to the presentation. I already explained these problems of the input of stirrups for torsion, so we can proceed. Now we have the problem which I mentioned at the beginning in the questions, pre-stressed sections at inflection points with zero bending moments. I just repeat what are the sections with tendons approximately in the middle of the cross-section. I moved the tendons from the extreme position here to document it. All the cross-section is therefore in the compression, and tensile resultant force is close to the tendons, so we have small lever arm. We can possibly go directly to the example, pre-stressed cross-section all in compression. I open it. So maybe we can see the reinforcement as it is here, internal forces. We have several extremes. In the first extreme, I applied the variable bending moment 2500. So when we have these internal forces in extreme E1, we can see the response. Go to results, response, and I let the program draw all the initial state, then total response, response on total internal forces, both permanent and variable. I explained what the initial stresses are and strains during last session. And there is also an increment, which is the green one, between which is we get it when we subtract initial from the total effect. You can see that for this 2,500 kilonewton meters, we get quite nice flexure, I would say, or quite nice distribution of the strains, this plane of strain of the increments that loads this section in flexure. Therefore, we are able to calculate the lever arm. Can increase it again, and we see that we have this lever arm calculated. We can also see it in shear. This here because we have only single bending, we have exactly the same number, and it is calculated from the response, no problem. And if we go to next extreme, I see the internal forces, that the variable bending moment changed from 2500 to 1750. When we see the response of such internal force or such bending moment, then we get this plane of strain increments a little bit different, but there is still some, I would say, bending or flexure in this incremental plane, and we can again calculate the lever arm and use it for shear here, and we identify BW, and there is no problem with the design. Let's go to third extreme, and I decrease the bending moment to 1000. We go to results, response, and now even the incremental plane of strains is in compression. So we cannot find the lever arm, and in that case we have to calculate it, and we take default value from code settings of lever arm. Okay, so what is the conclusion from that? I would like to explain what is the way of determination of these parameters in pre-stressed section in our program. You saw it in the example, but let me to explain the theory a bit. First of all, we want to do it in standard way. Usually in old books we learned that the pre-stressed section should be converted into non-pre-stressed. That's a simple case that we can solve, and we can do it via decompression state. So we calculate the response on those three internal forces N, My, Mz, and we determine the state of decompression. This is the state here when we have sigma C, stress in concrete, 0. Theoretical case, which is actually in statically indeterminate structure, you would hardly get it, but in an approximate way or with some simplifications we can calculate it. Then we calculate the plane of strain increments. I explained that was the green line or green picture. We calculate this plane of strain increments starting from the state of the decompression. So it is increment from the state of decompression. And if the plane indicates flexure, that was the case of extreme 1 and 2, then we calculate lever arm exactly according to Eurocode. If the plane indicates compression, then the lever arm is taken from code settings, but you can definitely change it. We should probably note that the plane of strain increments, which is shown here in RCS, is not exactly the plane. Here we have of strain increments starting from the state of decompression. We have this plane starting from initial state, which I explained last time, but they do not differ too much. You can see the last session for the explanation of initial state. So this is only explanatory picture, not exact picture, because this is not a decompression state. We calculate it, but we do not display it. Okay, so this is the explanation how we determine Z and D in pre-stressed sections. Actually, this was a difficult, I would say, a task for us to derive it. And now we come to the interaction of internal forces. You see the explanatory picture, which is very simple, and it explains that the forces which we get from the flexure here and the forces in longitudinal reinforcement which we get from shear analysis, shear design, we can simply add and check. We do it, then we can even draw such nice interaction diagram between bending moment and shear force. This is calculated in Excel file. But we do not do it in this simple way. This is not very suitable for numerical analysis, and it is nice to explain the theory or the principle, I would say, but not to use it practically. That's why we performed, before we did it, we made this study of possible approaches to consider the interaction. We take this example of standard beam 600 millimeters deep. We have 4 bars of diameter 20, and we loaded this cross-section by external moment 210 kilonewton meters and shear force 150 kilonewtons. First of all, we calculated the response for these forces. You can see that we are quite, I might say, more than 100 megapascals below the plastic branch of stress-strain relationship, and here we have approximately 10.7 megapascals compression in concrete and some compression in steel. First, which comes to our mind, of course, to respect the effect of shear is the shift rule. Everybody knows shift rule in Holland. I remember that I was asked many times by Dutch customers about it. So we tried to calculate the increase of bending moment. This is 210, we have 283, and we applied higher bending moment exactly according to shift rule. We really got the increase in tensile reinforcement, which was expected to plastic branch, but in compression, due to the bending moment, which is higher, we even applied higher compression. This is almost 17 megapascals compared to 10.7, which is not a real behavior. Actually, in this picture, it is clearly shown that we apply a tensile force, not the compression. So also this reinforcement is loaded more in compression. So that's why we didn't want to apply it, and we tried other approach to apply normal force. So we evaluated the normal force going to longitudinal reinforcement and it is induced by shear. We applied it, and in that case the whole section resisted. That's why we even didn't get to plastic branch here in the tensile reinforcement, and we decreased the compression in concrete, which actually we didn't want, because we didn't want to use the compression reserve of the compression zone. As I explained before, the angle between the resultant forces in shear and in bending moment can differ significantly, and then there is an uncertainty if we really can use the compression reserve, or if we apply the tensile force caused by shear in the compression zone or not. That's why we choose different approach, and this is the one. We actually calculate the strain caused by the shear, strain in the longitudinal reinforcement, and the plane, actually the strain in longitudinal reinforcement caused by this tensile force is added, or better said, the tensile capacity of the reinforcement is decreased by this strain, and the response of forces to normal force bending moments is found. So it is like if we subtract this strain calculated for shear force, acting shear force, and we subtract it from the stress-strain relationship. Then we calculate the response and we check the total strain against the limit value, and also the stress is calculated and checked, and it is calculated with respect to stress-strain diagram, so it is non-linear. We believe that the procedure is a reasonable interpretation of variable angle truss model, even if we know that it is not a calculation of virtual reality. But we hope this is an approach which corresponds with this variable angle truss model. The last example which I want to show is the example of limited remaining capacity of longitudinal reinforcement. I used similar examples in the study. I will open this interaction CSS. Interaction CSS. Okay, we have the reinforcement. You see standard cross-section, internal forces. This is quite important because we will change the internal forces. We have only shear force in vertical direction 90, then some torsion 20, bending moment 145 in Y, around Y-axis, and MZ is 20 kilonewton meters. If we go to results and we go to interaction, we can see the response, of course. Now we have 318, we go to interaction, then this becomes bigger, and we use the reserve of the longitude, or in the strength of longitudinal reinforcement. But what we want to see is the warning, because we can see that the interaction is used, the utilization is 106%. From this table we can see, I can again make it bigger, we can see that it is the check of the interaction of the shear force and torsional moment. And we go to the non-conformities. Torsion check is not satisfactory due to insufficient strength of concrete, and the paragraph. And also, shear check is not satisfactory due to insufficient strength of shear reinforcement loaded by combination of shear and torsion. And here the clauses of Eurocode. So the section is not satisfactory because we applied the formulas defined by Eurocode, and this is not actually a theory which I explained, but I wanted to show this way, or this example of the loading. We go to internal forces and we change the extreme to the second one, and we see that bending moment and torsion is still the same, but the shear force decreased. So we can get the same response. There should be no change, 318, but the interaction now is satisfactory because the interaction of shear force and torsional moment is now 99.6%. There is a non-conformity. Check of interaction according to 6325 is not satisfactory, but this is only about the concrete strength. So it doesn't influence the total strength if we have a reinforcement. This is only TRDC and VRDC. So this is okay. And now we have this satisfactory check, and we go to internal forces. You can see them before I make the change, and after I make the change in the third extreme, I increased the bending moment from 145 to 200. So the longitudinal reinforcement is utilized more. Now you can see that we get this stress in this reinforcement. This is most tension reinforcement, and this is already, if I go to diagram, this reinforcement is already on plastic branch. Okay, so it is used more. And then if we go to interaction, we see that we have 1000. and it is Vt plus m, it is 1000, and we can read the message. It is not possible to resist the force caused by torsion in longitudinal reinforcement. Satisfactory amount of longitudinal reinforcement is not inside the stirrup used for torsion resistance, or longitudinal reinforcement is fully used by combination of normal force, flexure effects, and shear force. So you should increase the amount of longitudinal reinforcement. So this is the non-conformity message. This is the advice what to do with the section to get it satisfactory. So I showed the example of the interaction check when the longitudinal reinforcement is, I would say, fully utilized, or there is small remaining capacity of the reinforcement. So that's all for today, and I would like to ask if there are any questions, and I suppose there are.
Not so far. Please feel free to input any in questions tab.
Mm-hmm. If you don't have any questions, we can of course answer your question which you send us by email, and that is also possible. And we will we made the recording, and the recording will again appear on YouTube. So you can go through the session again, and if you get any idea what to ask and how to comment, then I would be very happy to answer all your questions.
So one came.
You do have bend-up bars.
Yes.
Mm-hmm. Yes, we do. We have bend-up bars, but only in case of non-pre-stressed sections in RCS. We can analyze, or we can check the strength of the section in RCS for bent-up bars. We can show it some other time. I do not have the example prepared, but it is possible. Any other question?
If you have a shear check for fatigue as well.
This is we do check the fatigue strength of the concrete diagonal strut. According to Eurocode, there is one clause which I remember. So we do check it in our fatigue check. Yes, and also stirrups. Mm-hmm. So any other question? Do you have special rules for circular cross-section? Unfortunately, we don't. If we speak about this problem of shear in circular section, then the only way how to solve it is via this. We go to reinforcement and reinforcement editor, and as I showed, this user settings cross-section. Then we can play with it, and the user can estimate what is the lever arm and all those things. We are thinking of the possibility to improve this solution, which would also improve the possibility of identification of the, I would say, layers, or better said, we would not identify the layers because there are no layers in circular cross-section for crack width, and then we would be able to find the effective embedment zone for individual bars. But this is something which we have to develop some numerical tools, which we probably will have to develop in our currently ongoing project, DR design. And when we have it, we can implement it also into RCS. But this will definitely not be this year. We have to, this is a long-term development, and I'm sorry, at the moment we can do it via this estimates of user-defined parameters. There is some other question which I cannot read properly. Do you have a method for design of reinforcement around openings using stratum type theory? Not yet, but we, as I mentioned, this DR design project, ongoing project, we will have this possibility. It will be very similar to our steel connection in the way we do it, and we will have a prototype of the program in April. We would be very happy to collaborate and to discuss the improvements and the way we do it with you. We also can do it when we have a Dutch roadshow in April. I will go to Netherlands and we visit a couple of customers. Then we can also discuss this this functionality. So we believe in it very much. And it will not be based on stratum type purely. We have better solution, better approach. We will be able also to check the crack width and other SLS checks. So any other question? So we have exactly 4 o'clock and there are no questions, so I think we can thank you for your attention, and we will see each other, I hope, in the next and last spring Dutch session, which will be approximately in 2 weeks. Thank you very much, and bye-bye.